previous lecture I discussed single slit and double slit Fraunhofer diffraction. Now I am going to discuss in this lecture Fraunhofer diffraction pattern of n parallel slits, each of width V and separated by equal opaque spaces A as shown in this figure. This type of arrangement is known as diffraction grating. We will see that the diffraction pattern gets modified as the number of slits is increased beyond 2. Let a plane wavefront of light of wavelength lambda be incident normally on the slit as shown in this figure. According to the principle of Huygens Fresnel, at the instant the incident wavefront occupies the plane of the slits, every point in each slit is regarded as the origin of secondary spherical wavelets, which is spread out in all directions. Therefore, the rays are diffracted from each slit in all directions. If capital A is the resultant amplitude of light from a single slit along the normal to the plane of the slits, then resulting amplitude in a direction making an angle theta with the normal will be capital A sin beta by beta, where beta is equal to pi by lambda b sin theta. Therefore, in the case of n parallel slits of equal width, we can replace all the secondary wavelets in each slit by a single wave of amplitude capital A sin beta by beta, starting from its middle point like S1, S2, S3 so on, and travelling at an angle theta with the normal. Let us now find the resultant effect of these n vibrations when brought to focus by a convergent lens. To calculate the path difference between the diffracted waves from successive slits, from S1 we draw perpendicular S1 k n minus 1 on the parallel paths of these vibrations. Then the difference of paths S1 P1 and S2 P2 is S2 K1, which is equal to A plus B sin theta, and hence phase difference phi would be 2 pi by lambda into A plus B sin theta. Similarly, the difference of paths S1 P1 and S3 P3 is S3 K2, which is equal to 2 times A plus B sin theta, and hence the phase difference will be 2 phi. Similarly, we can calculate the phase difference between the other diffracted waves. Thus, if at the instant the waves under consideration arrive in focus, we consider the phase of the wave from S1 to be 0, then the phase of waves from S2, S3, S4 so on should be phi, 2 phi, 3 phi etc. That is, the phases increase in arithmetic progression. Therefore, the problem reduces to find the resultant amplitude of n waves of equal amplitude A sin beta by beta and equal period, but the phase increasing in the arithmetic progression, the common phase difference being phi. Therefore, the resultant amplitude R will be equal to A sin beta by beta into sin n phi by 2 divided by sin phi by 2, where A sin beta by beta is the amplitude of single slit and beta is equal to pi b sin theta by lambda. If we write phi by 2 equal to gamma, which is equal to pi by lambda into A plus b sin theta, then the resultant amplitude R will be equal to A sin beta by beta sin n gamma divided by sin gamma. Therefore, the intensity of the resultant wave will be equal to A square sin square beta by beta square sin square n gamma divided by sin square gamma. Now, here if we put n is equal to 1 and n is equal to 2 in this expression, we will find the result which we have already obtained for single slit and double slit diffraction pattern respectively. Further, the first factor in this expression, that is A square sin square beta by beta square, simply gives the intensity distribution in the diffraction by a single slit. The second factor, sin square n gamma by sin square gamma, may be said to give the interference pattern for n slits. Thus, we can say that each of the n slits give rise to diffracted beam in which the intensity distribution depends on the width of the slit, and the diffracted beam then interfere with one another to produce the final diffraction pattern. Now, we can find out from this expression the position of maximum and minimum intensity on the screen, that is at the focal plane of the lens. Now, from the intensity equation, I is equal to I naught sin square beta by beta square into sin square n gamma upon sin square gamma, we can write the condition for principal maxima, that is where the intensity is maximum. So, intensity will be maximum when sin is gamma is equal to 0, that is gamma is equal to n pi, where n is equal to 0, 1, 2, 3, etc. For these value of gamma, both numerator and denominator of sin n gamma by sin gamma vanish, that is term becomes indeterminate, but it may be evaluated by finding its limit as gamma tend to plus minus n pi. So, by method of calculus, we can find the limit gamma tending to plus minus n pi sin n gamma by sin gamma equal to plus minus capital N, where capital N is the number of slits. Therefore, the intensity of the principal maximum is proportional to capital N square, which increases with the increase in the number of slits. The intensities of principal maxima are, however, modulated by the single slit diffraction pattern. The actual intensity is obtained by multiplying capital N square with single slit pattern. Therefore, intensity of principal maxima is given by n square into I naught into sin square beta by beta square, where beta is equal to pi by lambda into b sin theta. Actually, at the principal maxima, the field produced by each of the slits are in phase, and therefore, they add up, and the resultant field is n times the field produced by each of the slits. So, for principal maxima, we have gamma is equal to plus minus n pi. So, this condition we can write in terms of a and b, that is pi by lambda into a plus b sin theta is equal to plus minus n pi, or sin theta equal to plus minus n lambda upon a plus b. Since sin theta is less than or equal to 1, so we should have n lambda less than or equal to a plus b. So, values of n should be such that n lambda should be less than or equal to a plus b. Therefore, for principal maxima we have A plus B sin theta equal to plus minus n lambda. This equation simply expresses the condition that if the difference of paths of the parallel diffracted rays from any pair of corresponding points of grating is integral multiple of lambda, then all the parallel diffracted rays in that direction reinforce so as to form the principal maxima in the focal plane of the lens. The whole number n in the above equation represents the order of the interference maximum, and physically it gives the number of wavelengths in the difference of paths of the diffracted rays from any pair of corresponding points of the grating, as shown in this figure here. The distance A plus B is called the grating element. Above equation does not contain capital N, so that for a given slit separation the position of the principal maxima are independent of the number of slits. Now, we can find out the position of minimum intensity from the expression of intensity. So, the value of gamma for which only the numerator of the term sin n gamma upon sin gamma vanishes give point of 0 intensity in the diffraction pattern. That is, for minima we should have sin n gamma equal to 0, but sin gamma should not be equal to 0, or we should have n gamma is equal to plus minus m pi, where m has any integral value with the exception of 0, capital N, 2 times capital N, 3 times capital N, so on. Because for these values of m, gamma is equal to 0, plus minus pi, plus minus 2 pi, plus minus 3 pi, so on, and therefore, the denominator of the term sin n gamma upon sin gamma also vanishes. This corresponds to the position of principal maxima. So, condition for minima is capital N pi by lambda into A plus B sin theta equal to plus minus m pi, or A plus B sin theta equal to plus minus m upon capital N times lambda, but m should not be equal to n times capital N, where n small n has integral value 0, 1, 2, 3, so on, and this n gives the order of principal maxima. Thus, for minima we have A plus B sin theta equal to plus minus lambda upon capital N, plus minus 2 lambda upon capital N, plus minus 3 lambda upon capital N, so on. Omitting the values A plus B sin theta equal to 0, plus minus capital N lambda upon capital N, plus minus 2 times capital N lambda upon capital N, so on, which are the condition for principal maxima. Now, so we have found the condition for principal maxima and 0 intensity in the diffraction pattern. From this we can say that between the principal maxima of 0 order and the principal maxima of order 1 there is n minus 1 equal spaced points of 0 intensity, that is minima. Hence, there are n minus 2 other maxima known as secondary maxima between any two adjacent principal maxima. Thus, for 3 slits there are only 1, for 4 slit there are 2, and for 5 slit there are 3 secondary maxima. To find the position of secondary maxima, we first differentiate sin n gamma upon sin gamma with respect to gamma and then equate it to 0. Thus, if you differentiate this sin n gamma by sin gamma with respect to gamma and after equating it to 0, we will find capital N tan gamma is equal to tan capital N gamma. The root of this equation other than gamma is equal to plus minus n pi give the position of secondary maxima. The secondary maxima are not of equal intensity and intensity decreases gradually as we go out on either side to any principal maxima. Moreover, they are slightly shifted as in the case of single slit pattern towards the adjacent principal maxima. Now, the plot of sin square n gamma upon sin square gamma is shown here for n is equal to 6. From this figure we can see that there are 4 secondary maxima between any two adjacent principal maxima which we have already discussed. Here it should be noted that the intensities of the principal maxima are modulated by the single slit diffraction, that is the plot of sin square n gamma upon sin square gamma is multiplied by I naught sin square beta by beta square, the single slit diffraction pattern. When n is very large, that is when the number of slit is very large, the principal maxima will be much more intense in comparison to the secondary maxima. A particular principal maxima may be absent if it corresponds to the angle which also determines the minimum of the single slit diffraction pattern. This will happen when a plus b sin theta is equal to n lambda and b sin theta is equal to m prime lambda, where m prime is equal to 1, 2, 3 so on, but m prime is not is equal to 0 are satisfied simultaneously and is usually referred to as a missing order. Although the principal maxima occurs at the same position with 3 and 4 slits as with the 2, but they become brighter and narrower while the secondary maxima become weaker and faint with the increase in number of slits. This is clear from this figure. The extension to a very large number of slits, as in actual grating say 15,000 lines per inch, the maxima become very narrow and of sharp intensity, while the secondary maxima are of negligible intensity invisible in the pattern. Now, we can easily deduce the angular separation between the first minima on either side of the principal maxima in the diffraction pattern of any order say n. This angular separation is called the angular width of the principal maxima in the nth order. Let theta n be the angle of diffraction corresponding to the principal maxima of wavelength lambda in the nth order. This direction is given by a plus b sin theta n equal to n lambda, or if we multiply capital N both sides, we will get capital N times a plus b sin theta n equal to capital N into small n into lambda. The position of minimum of intensity in the diffraction pattern due to n slit are given by the condition a plus b sin theta is equal to lambda by capital N to lambda by capital N so on, or capital N into a plus b sin theta equal to lambda or 2 lambda or 3 lambda, but for the values capital N into a plus b sin theta equal to 0, capital N lambda or 2 times capital N lambda, we get respectively first, second, so on order of principal maximum. Thus, the first minimum on either side of the principal maximum of first order is given by equation capital N a plus b sin theta 1 plus minus d theta 1 equal to capital N lambda plus minus lambda, where the angle of diffraction theta 1 corresponds to the principal maximum of first order and theta 1 plus minus d theta 1 corresponds to the first minimum on either side of this maximum. Now, it should be obvious that the first minimum on either side of the principal maximum of nth order should be given by capital N into a plus b sin theta n plus minus d theta n equal to small n into capital N into lambda plus minus lambda. So, where theta 1 plus minus d theta n is the angle of diffraction corresponding to first minimum. So, by using the previous two equations, we can write sin theta n plus minus d theta n divided by sin theta n equal to small n into capital N into lambda plus minus lambda divided by small n into capital N into lambda, or sin theta n plus minus d theta n cos theta n divided by sin theta n equal to 1 plus minus 1 over small n into capital N, or we can also write d theta n equal to 1 over small n into capital N cot theta n. This equation expresses the half angular width of the principal maximum of order n. We have a plus b sin theta n is equal to n lambda. So, we can write order of diffraction n equal to a plus minus b sin theta n divided by lambda, or d theta n will be equal to lambda upon n into a plus b sin theta n into cos theta n divided by sin theta n, which we can simplify and we will get d theta n is equal to lambda upon capital N into a plus b cos theta n. Now, here capital N into a plus b is the total width of the ruled surface of grating. Thus, the sharpness of the principal maxima, that is a smaller value of d theta n, depends upon the total width n into a plus b of the ruled surface of grating and not upon the number of lines per centimeter. Now, I am going to describe how gratings are fabricated for laboratory use. As we know, an arrangement of a large number of equidistant slits is known as a diffraction grating. For narrow principal maxima, that is sharper spectral lines, a large value of capital N is required. A good quality grating therefore requires a large number of slits, typically of the order of 15,000 per inch. This is achieved by ruling groups with a diamond point on an optically transparent sheet of material. The groups act as opaque spaces. After each group is ruled, the machine lifts the diamond points and moves the sheet forward for the ruling of the next group. Since the distance between the two consecutive groups is extremely small, the moment of the seat is obtained with the help of the rotation of a screw which drives the carriage carrying it. Further, one of the important requirements of a good quality grating is that the line should be as equally spaced as possible. Consequently, the pitch of the screw must be constant. Commercial gratings are produced by making the cost of an actual grating on a transparent film like that of cellulose acetate. Now, we will discuss about the grating spectrum. So, the condition for principal maxima in the diffraction pattern of plane grating when light is incident normally on it is given by a plus b sin theta equal to plus minus n lambda. When the number of ruling is very large, say 14,000 to an inch, and the primary source of light is a narrow slit, the principal maxima are observed as sharp bright lines in the focal plane of the eyepiece of the telescope adjusted for the parallel range. Consequently, the principal maxima are commonly spoken as spectrum lines. If the slit is parallel to the rulings of the grating, the spectrum lines will be also parallel to the rulings. These lines are simply the images of the slit. It is clear from the above equation that in a given order n, the angle of diffraction theta depends upon wavelength lambda. Therefore, if the source gives light of number of wavelengths, that is lambda 1, lambda 2, lambda 3, so on, then in the given order except n is equal to 0, we will find as many lines as there are different wavelengths in the light source. Thus, a line spectrum is formed in each orders, but for the central image, that is for n is equal to 0, the path difference is 0 for every wavelength. Hence, the central maxima of different wavelength coincide, forming the central image obviously of the same color as that of the primary source of light. On the other side of the central image, a similar set of spectra are formed. In each order, the spectrum line corresponding to shortest wavelength is formed on the side towards the central image. Now, let us see how to determine the wavelength of light by using the grating spectrum. So, we have a plus b sin theta n is equal to plus minus n lambda. So, here n is the order of the spectrum and a plus b is the grating element, and if capital N is the number of lines per centimeter in the grating, then we can calculate a plus b equal to 1 over capital N. Thus, by noting the value of n, that is order of the spectrum, and measuring the angle of diffraction for a definite spectral line, we can easily calculate its wavelength. So, this angle theta is measured by using a spectrometer in the laboratory. So, to determine the value of wavelength by using grating, we have to measure experimentally the diffraction angle theta, and then by knowing the order of the diffractions, and then using this equation a plus b sin theta is equal to n lambda, we can calculate the value of wavelength. Now, let us discuss about the overlapping of orders. So, when we examine a large range of wavelengths with the help of diffraction grating, then some overlapping of spectral lines occurs in the higher order of spectrum. This is due to the reason that for a given value of theta, the fundamental equation of grating, that is a plus b sin theta is equal to n lambda, may be satisfied by the several values of lambda with appropriate values of n. For example, if you have a plus b sin theta is equal to lambda 1 equal to 2 times lambda 2 is equal to 3 times lambda 3, so on, then the spectral line of wavelengths lambda 1, lambda 2, lambda 3, so on, occurring in the first, the second and the third orders respectively will coincide in position in the spectrum, that is they will overlap. Now, let us calculate the angular dispersive power of the grating. The angular dispersive power of the grating is defined as the rate of change of the angle of diffraction with the change in wavelength. Mathematically, it is expressed by d theta by d lambda, and its value can be very easily obtained by differentiating equation a plus b sin theta equal to n lambda with respect to lambda, keeping n constant. So, angular dispersive power d theta by d lambda will be equal to n upon a plus b cos theta. So, this equation shows that the angular dispersion is directly proportional to n, the order of the spectrum. This means that the angular separation d theta between the principal maxima corresponding to wavelength lambda and lambda plus d lambda increases with the order of the spectrum. Therefore, the second order spectrum is twice as wide as the first, and so on. The angular separation d theta for a given d lambda is inversely proportional to a plus b, the width of the grating element, and therefore directly proportional to the number of lines per centimeter on the grating. The smaller is the grating element, the greater is the spread of spectrum of given order. The angular dispersion increases with theta and therefore with the wavelength, since theta increases with increase in lambda. Therefore, grating spectrum are spread much more at the red end than at the blue end of the spectrum. Now, let us consider the plane wave front of light of wavelength lambda is incident obliquely on the grating at the angle of incidence I as shown in this figure. For a set of parallel rays diffracted at an angle theta with the grating normal, it can be shown that the difference of paths of the diffracted rays from the corresponding point of grating is a plus b into sin I plus sin theta. Therefore, in this case the condition for principal maxima becomes a plus b into sin I plus sin theta equal to n lambda. So, this is the condition for principal maxima for oblique incidence. For the other side of the direct beam, the condition for principal maxima in case of oblique incidence will be a plus b sin I minus sin theta is equal to n lambda, where n is equal to 0, 1, 2, 3, so on. Now, we will discuss briefly about the concave grating. So, we have seen that the plane grating requires the use of two convergent lenses for the formation of spectra, one for rendering the light incident on the grating parallel and the other for bringing the parallel diffracted rays in focus. But the glass lenses are not suitable for investigation of ultraviolet region because they are not transparent outside the visible spectrum. Also, the lenses cannot be made truly achromatic, and hence chromatic aberrations comes in the spectra. To remove these problems, concave grating has been developed. In this case, the grating, instead of being ruled on a plane surface, is ruled on a concave spherical mirror of metal, so that it diffracts and focuses the light at the same time. This will eliminate the chromatic aberration and can be used in ultraviolet region. So, if R is the radius of curvature of the spherical surface of the grating, a circle of diameter R can be drawn tangent to the grating at its mid point, which defines the locus of points where the spectrum is in focus, provided the source slit also lies on this circle as shown in this figure. This circle is called the Roland circle and the mounting is known as Paschen mounting. So, till now we have discussed single slit, double slit and multiple slit diffraction pattern. Now, I am going to discuss about the resolving power of certain instrument like grating, telescope and microscopes. So, let us first discuss how the diffraction phenomena limit the resolving power of the instruments. So, the upper limit to the useful magnification by any instrument is set by the fact that the image of the point source formed by the lens, even in the absence of all aberrations, is not a point image, but in reality it is a circular diffraction pattern formed by the limited portion of the wavefront transmitted by the lens system. This diffraction pattern is characterized by the central bright disk bordered by the dark and the bright concentric circular rings of rapidly decreasing intensity. An optical system is said to be able to resolve 2-point objects if the corresponding diffraction patterns are sufficiently small or sufficiently separated to be distinguished as separate image patterns. With the analyzing instruments, we are mainly concerned with its ability to just separate in the diffraction spectrum two spectral lines corresponding to light of slightly different wavelengths lambda and lambda plus d lambda. Now, let us discuss about the Rayleigh criteria for the limit of resolutions. From a detailed study of the resultant intensity distribution in the diffraction pattern of closely spaced point sources, Lord Rayleigh arrived at the conclusion that two equally bright point sources could be just resolved by any optical system when their distance apart is such that the central maximum in the diffraction pattern due to one source coincided exactly with the first minimum in the diffraction pattern due to the other. This is known as Rayleigh criterion of resolution, and it is also applicable to the resolution of spectral lines of equal intensity formed by grating on the prism spectrograph. When applied to spectral lines, it is equivalent to the condition that in the diffraction pattern, the angular separation between the principal maxima of two spectral lines in a given order should be equal to half angular width of either principal maximum. This means that if the principal maximum of wavelength lambda is formed by an optical instrument at an emergent angle theta and the principal maximum of lambda plus d lambda in the same order is formed at an emergent angle theta plus d theta, then the first minimum in the diffraction pattern due to lambda should also be formed at an angle theta plus d theta. The physical significance of Rayleigh's criteria for resolution can be explained by considering the resultant intensity distribution in the diffraction pattern due to two wavelengths lambda and lambda 1. Let the wavelength difference be such that the principal maxima of one falls exactly over the second point of minimum intensity in the diffraction pattern of other. The two wavelengths must have been emitted by different sources so that the disturbances are incoherent. Consequently, the total intensity at any point in the spectrum is simply the sum of the intensities for each wavelength. In this case, there is a distinct point of zero intensity in the middle of the resultant intensity curve, which has been obtained summing the intensities due to separate pattern. Thus, the two spectral lines are distinctly separated. Hence, if the wavelength difference is smaller, the two spectral lines with their principal maxima are closer. There is one limiting value of lambda 1 equal to lambda plus d lambda, for which the angular separation between their principal maxima is such that the principal maximum of one falls exactly over the first point of minimum intensity in the diffraction pattern due to the other. Therefore, the intensities of maxima in the resultant intensity patterns are equal to those of original maxima. Thus, the resultant intensity curve is a double humped curve with a distinct dip at a point halfway between the two principal maxima. This change of intensity is easily visible to the eye and enable us to recognize that in the resultant pattern there are two spectral lines corresponding to lambda and lambda plus d lambda. The two spectral lines under this condition are said to be resolved. But if lambda 1 is less than lambda plus d lambda, the two spectral lines come still closer and the intensity curves of the principal maxima show considerable overlapping. The resultant intensity curve exhibits no dip but only one maximum in the center, thereby indicating as if it is a diffraction pattern of only one spectral line. Thus, under this condition, the two spectral lines are not resolved in their diffraction pattern. Hence, for two spectral lines to be resolved, it is absolutely essential that the least angular separation between their principal maxima should be such that the principal maximum of one should fall on the first point of minimum intensity of the other. Now, let us use this Rayleigh criteria to derive the expression for resolving power of a grating. The function of an analyzing instrument like grating is to resolve two images of the same slit formed by light waves of slightly different wavelengths, say lambda and lambda plus d lambda. The images of the slit are known as the spectral lines corresponding to wavelength lambda and lambda plus d lambda. Accordingly, the limit of resolution of a grating is defined as the smallest wavelength difference for which the spectral line can be just resolved at the wavelength lambda. This limit of resolution is mathematically expressed by the ratio lambda to d lambda. Now, let a plane wave front of light to be analyzed be incident normally on the grating, which forms the diffraction pattern in the focal plane of the telescope lens corresponding to each of the wavelengths, say lambda and lambda plus d lambda, present in the incident light. The angular deviation theta n of the center of principal maximum formed in the nth order by light of wavelengths lambda is given by a plus b sin theta n is equal to n lambda, where a plus b is the grating element. The angular separation between the centers of the principal maxima corresponding to wavelength lambda and lambda plus d lambda formed in the order n is obtained by differentiating above equation with respect to lambda. So, we get a plus b cos theta n d theta n by d lambda is equal to n, or d theta n is equal to n d lambda divided by a plus b cos theta n. The half angular width of the principal maximum of lambda in the nth order is therefore d theta n is equal to 1 over n into n cot theta n, where capital N is the total number of lines in the grating. Now, according to the Rayleigh's criterion for resolution, the two spectral lines will be just resolved when the principal maximum of one falls exactly over the first point of minimum intensity of the other line. This condition will be realized if the angular separation d theta n between the two principal maximum is exactly equal to half angular breadth of the principal maximum of lambda in the same order. So, 1 over n capital N into small n cot theta n should be equal to n d lambda upon a plus b cos theta n. With the help of this equation, we can write lambda upon d lambda is equal to capital N times n, which is known as the chromatic resolving power of grating. So, the resolving power is directly proportional to the order n, and in the given order it is proportional to the total number of lines effective in the formation of diffraction pattern. It should be observed that the resolving power is independent of the spacing a plus b of lines. We have small n is equal to a plus b sin theta n by lambda. So, we can also write the resolving power lambda upon d lambda equal to capital N times a plus b sin theta n upon lambda, which we can write equal to w sin theta n by lambda, where w is equal to n capital N times a plus b, which is the total width of the ruled surface of the grating. Thus, a change in the number of lines capital N in a given width of ruled surface will not affect the resolving power. However, a change in n capital N would change the order n of the spectrum in a given directions. Since sin theta n is less than 1, the resolving power of a grating cannot exceed w by lambda. So, if we have to resolve the D1 and D2 lines of wavelength 5890 angstrom and 58966 angstrom of sodium by plane diffraction grating, the number of ruling N should be at least of the order of thousands. Now, let us calculate the resolving power of a microscope. So, the primary function of a microscope is not to magnify an object, but to reveal those finer details in the object which are invisible to an unaided eye. The extent to which finer details are revealed depends not on the magnifying power, but on the resolving power of the microscope. Resolving power of a microscope is conveniently expressed in terms of the smallest linear separation between 2 points object which are just resolved, that is, their diffraction patterns formed by the microscope objective are just distinguishable. The smaller is this distance, the greater is said to be resolving power. Let us derive this least separation between the 2 point object for 2 distinct cases. Number 1, the object are self luminous having no phase relations. Number 2, objects are not non-luminous, but their illumination is coherent. So, let me summarize what I have discussed in this lecture. So, in this lecture I discussed the diffraction pattern of N slit, and I discussed how to use grating spectrum to calculate the wavelength of light in the laboratory, and then I discussed the Rayleigh criteria for resolution and derived the expression for resolving power of grating. In the next lecture, I will discuss about the resolving power of microscope and telescope, and I will also solve some numerical problem related to single slit, double slit and multiple slit Fraunhofer diffraction. Thank you.